Welcome back, humans and robots alike. Today we'll be talking mainly about LiDAR-based SLAM. It's going to be a short introduction to it. I will cover some important points, but I would again urge the viewer to actually go and look at the code bases of any LiDAR-based SLAM method to understand in more bit detail how individual components are coded and structured. So we'll mainly look things from more of a conceptual way with little bit of math here and there. So yeah, let's get started. So initially we talked about this odometry, right? And I had told in the last lecture that oh, you will use LiDAR odometry or visual odometry. So how do we do that? So how do we find our motion estimation with just a LiDAR? Seems weird and cool at the same time, how you would end up doing it. Now, odometry is important, and finding different sources of that odometry would only improve your system. So what you end up first doing is you take a full scan of your LiDAR. So full scan of LiDAR is basically if the if this is like my drone and I have a LiDAR pointing towards, I have a rangefinder pointing towards this. It goes all around and then comes back to the same position. Now it could be a 3D LiDAR, so I will get all the 3D points of this space and again come back to the same position. So one full scan or one full sweep of my field of view for a LiDAR is called as like a full scan being built. Now, there are three parts to finding this visual odometry. First, you need to do motion compensation. We'll look why that is the case and how we fix it. Then we need to do a correspondence search. So between one scan and another scan, how do I know that, okay, let's say these are two scans, right? How do I know my index finger is this index finger or not? Who says that? Why can't I match my scans like this? So the reason why you first of all, okay, let me first explain why you would like to match the scans also in the first place is, so if you know that this scan and this scan exist, and I want to merge them together, so okay, in this case, because the left and right hand, let's keep it this way. I want to merge them together. If I can estimate this translation and rotation, I know my motion the ego object did, right? And that's what we wanted to know. And now problem is, in a LiDAR scan, how do I figure out which are the two indexes I need to match, right? And so let's say now if I know this is my index, this is my index, this middle, ring, and pinky, I can find this and do the scan registration and then find my motion. But the correspondence search is also an important aspect in my overall pipeline. So that's clear, right? Now, as I spoke that a LiDAR would be here and it will do a full sweep, but you do realize that your object could be still moving. And even though the LiDAR in the previous lecture we saw there was LiDAR picture with 360, even though it seems like it's rotating very fast, but the object also moves very fast. Drones especially move quite fast if you want them to. So because of this, a scan could also end up with a bit of motion distortion. So let's look at that, right? So this is my sweeping LiDAR, and one would be stationary, and then I would be showing you a laser scan of what you would get if the robot was moving in a particular direction. So on the left, you can see the robot's motion, and then this is actually the scan what you would get. So the red is what we would like to have, but the blue is what we end up getting because there is a relative motion. Now, the speed at which the object is usually moving versus the speed or the rotational speed of my LiDAR dictates how much this distortion is going to be. But usually, LiDARs would be running at 10 hertz of rotation speed. A new scan comes at 10 hertz, so every one tenth of a second, you're going to find do one full revolution. Considering that if your speed is around even 30, 40, you could get a little bit of motion distortion for sure. 30, 40 kilometer, right? Uh, so that's a problem. So what people usually do is they will take the IMP reading or the motion estimation which you have from other sources use that to undistort this individual source of yours. And using that, I mean, you have to be a bit careful, right? You can't use some sort of a registration technique here as well, because it is a possibility that there was another drone in your observation space which was also moving fast in some other direction, right? And then if you are just using uh, point-wise registration technique, this could like ruin this undistortion which you have to do. So you will usually use some sort of a motion compensation. So using IMU or some other things to do that for you. All right. So let's say we undistort our motion. Next step is scanning, scan registration, and also that correspondence. So for now, let's just be be in our happy place where we have the correspondence, right, between the 2 points. So you have a source and then you have a target. So let's say this was a source and this was a target. You have a source and a target and you want to estimate this motion. You want to minimize basically the MSE error between these two sets. And let's say you have the corresponding points. What you will do is, oh, okay, I will just try R and different T's and then, I mean, that's one way to do it. Just do a full brute force search of R and T's and then figure out a way. Or I can be a bit clever about it. So what I would do is I will take centroid of these two sets. So centroid position of these two sets, use that to have this mu x and mu p. So these are my centroids. Find a difference between each of my points. So the um xi here is my uh, the point which I want to translate. So it's the target, means the source points which I want to get to the target, right? Now to do that, I'm subtracting the centroid from all the source points which I have and using going forward with it. So okay, so this was my new x, and then my new p is yeah, so the target space. So xi p will be my in all the points which I had, subtract all the points from the space, subtract my x, the centroid point from it. In P, in my target space, I'm subtracting all my target points with my new P, the centroid of my target space. When I do that, I get more of a shifted points, right? In a way, if you think about it. So let's put those into the MSE equation which we had earlier with little bit of rearranging. What we get is xi minus rpi, so that's the rotation part coming into play, and then this t, and minus t is the translation which we had to get. Now we know that mu x and mu p are related only by rotation because like I have almost removed right, and so, okay, so mu x and mu p are also going to be similarly rotated and similarly translated. So this point and this point are going to be similarly rotated and similarly translated. Because I know that fact, what I can do is I can rewrite this set of equations. So the t can be written with this, and then I can add it there. But that will like remove a bunch of points for me. So it helps us to simplify our minimization problem. And when we are left with only one variable, so you did all this math or rearranging so that we could go from minimization of two variables, R and T, and just come to R, right? So you first solve rotation, then you solve translation. That's the way we do it. We can solve this with SVD, and then output we get, we can finally get the translation output from it using this set of equation. Now, the problem which we had, which we didn't really want to get into till now, was the correspondence search or the correspondence. So, is this really my index? Is this their index? That is a big problem. So that's where this technique called as ICP, iterative closest point, comes into play. So here, what you do is, I mean, we are assuming that we don't translate too much between two sets of point clouds. When that is the assumption, we say that assuming two closest points, so a closest point to my source versus closest point to my, so between these two, because it's not going to, let's say, translate and rotate too much, the closest point for my index nail and the index nail of my right hand and left hand are going to tally. So I should be able to, in theory, get good correspondent matches as best as I can, right? So it's all as best as you can. So when I have that um, correspondent pairs between the two, the way I'm finding the relevant pairs is by just looking at the minimum Euclidean distance between the points. So that helps me with the matching part. And then when I have that, I can just try to solve it in the same way. So find the correspondence, find and apply the alignment. If there is a error which is beyond the threshold, then you redo the whole step again. So I mean, this is what that algorithm would look like in action. So you have a source, you have a target, right? And the lines in between them are the estimation the system thinks, okay, I think this is the right correspondence, this is the right correspondence between the target set and the source set. So let's see how it works. So what I've done here is the source set is rotated to left and then translated down a bit. So let's see it into action. Wow, it's amazing, right? How a simple algorithm could work so efficiently. But I would hold your horses right there. There's a problem. The problem is if there is too much of a rotation, you would end up with a bad answer. So what happens here is, uh, let me go back. What happened here now is, if you observe, this pattern is actually coming here. So what means is I have rotated even more down, right? Even more left to, I mean, anti-clockwise the sample and then again translate it in the same way. What that does is, because though ICP is rotationally invariant in terms of matching, but if you give it too much of rotation, it's going to fail. So what ends up happening is this top part of the source, which should have the top part of the source is actually here, and it should have ended up here. But because the rotation was so much and it is more of a symmetrical object, if you think about it, it because it's using MSE error and it comes to certain threshold, it predicted this would be a good match and it ended the loop. So it's not robust to large rotational changes, and this is a very big point of doing research in the ICP field. There are a lot of different ICP methods at this point who are trying to solve this in one way or the other. So inherently, that initial estimate which you have plays a very big role in the accuracy of your and the robustness of your ICP method. So it's a very important thing to note. So just showcase that. So how does a LiDAR slab look like? So this is how it looks like when you're trying to build. So this is that same aerospace map, which I think I showed in the initial few lectures. So this is how you're building that map, right? On the top right here, you can see the actual video on the video coming from the camera. It's not being used for any mapping purpose. It's just the LiDAR which is being used. And on the bottom right, you can see the map being built, right? Let me just go further. Yeah, so here you can see like that big map being. So again, it's running at a, a lot faster speed. So yeah, but this is the beauty of it, right? So another demonstration which I wanted to show was how can you deploy it on a drone. So what you see now here is the same aerospace department. You're trying to map it. So we've mounted the LiDAR on the drone, and then you're trying to map the overall environment using that. So this is, we flew from the terrace and then you can see the odometry coming from that. This is running at 5x speed again. You can see the trees being covered and it's beautiful how well, once the method starts working, how well it does work, right? Just fast forward it a bit. So you can see that top part. So again, like I said in the previous lecture as well, go look at the Google map and see if this structure which you see is the aerospace department or not. Right? It is, but you can just appreciate this map a lot more once you see the visual map from Google Earth or Google Maps from the top view. So with this, I'll end the slides for LiDAR SLAM. In the next few lectures, we'll look at Visual SLAM. All right, thank you. Bye bye.